So I want to let me start from the beginning and let's consider periodic table. And the key result that we need to understand is elements. And when I see elements, all elements in the entire universe that ever existed, that we discovered and that can be discovered, everything, right? Basically, entire matter is composed of elements, and we can, when we study elements, they have properties periodic in atomic number Z. That's basically how many protons you have in the nucleus. So here is the periodic table. I don't know if you can see it, but I think the details are not important, but I want you to see the overall structure. So basically, if you go this way, we are saying like a group, right? We are going from group 1, group, okay, these are, I think, nonsense. I don't know, my sources are messed up a little bit. So this is group 1, group 2, group 3, 4, 5, 6, 7, and 8. And if you go this way, we are saying these like periods. So this is period 1, period 2, period 3, period 4, period 5, all the way up to 7. I think everybody's familiar with this. There are like many things we can consider. For example, these, the first column is called alkali metals. By the way, most elements are metals anyways, I think. So this dashed line here, let me just draw it here, like this entire area is metal, and this area is non-metal. So you can see we have more metals than non-metals. So another very well known is like these are so-called inert gases. These are like group 8 inert gases. For example, helium, neon, argon, and so on. They are all inert gases. Whereas alkali metals are like lithium, sodium, potassium, rubidium, and so on. Another one that's, so these are like very well known, and they are going to fit into our description based on like atomic orbitals. So that's why I start from this, and I'm trying to set up the terminology. So these are so-called halogens. So like this is kind of like alkali metals, but we'll see they are actually like the anti-alkali metals. Like their properties can be understood pretty much the same way we understood alkali metals, but in the complementary way. So the one in blue here, this region is what we call transition elements, which hosts, for example, the metals you are probably more familiar, like I think iron is here, cobalt is here, nickel is here, copper is here, and so on. They're all here. And so here you can see like this structure presented is a little bit weird, but we are going to see that they are going to fit into hydrogenic orbitals. So these are, so all of these, like from like La, like from this La to I think ytterbium, I'm not sure what this is called, but they are almost chemically indistinguishable. That means they are almost the same thing in distinguishable, and we call them lanthanides. So these are lanthanides. So we also understand why they are chemically very similar. And the second one, these are the second row here is also very similar chemically, and we call them like actinides. Actinides. This is actinides. I'm not going to spell it right anyway, so the lanthanides are period 6, this is period 7. So in principle, in principle, almost everything we see, like not only the elements and atoms and like molecules, but in principle like more complex organic molecules and everything that's composed of atoms can be explained by everything can be explained by solving Schrödinger equation, right? You don't need to go and do anything, just solve it, look at the result, and it's going to tell you whatever you want, but this is not doable. For more than a few atoms, for more than a few electrons around the nucleus, we cannot solve it. We cannot solve it exactly, right? We have like spent plenty of time to understand like exactly solvable models. Like remember how complex it was even for the hydrogen atom, right? There was like all these like separation of variables, introducing some seemingly complicated rules for quantum numbers. And we looked at these orbitals, they look like pretty complicated compared to Bohr model. Now imagine we have to do this for 2 electrons, and 2 electrons are going to interact with each other. And now suppose 3 electrons and 4 electrons. Every electron is going to influence every other electron. So there will be like a very complex set of partial differential equations, and in general they cannot be solved. There are like some numerical schemes, but the message of this course will be there are like a lot of things we can understand without actually solving the Schrödinger equation. And for this we need approximations. And these approximations are going to be based on what we know about the orbitals from the solution of like simple hydrogen atom. Okay, so periodic table. Yes.
Can you roughly talk over one of the
So in principle, we have like some Hamiltonian that depends on like suppose we have like a fixed nucleus and n electrons. So this is going to be R1, R2, Rn, right? And this is what is the form of this Hamiltonian? Maybe I can try to write this. So for example, there'll be some kinetic energy of each electron. So we can write it like minus h bar squared over 2m sum over I is equal to 1 to n. Nabla, right? This is the complicated operator for each r. Each r has like r, theta, and phi, or x, y, and z, and each one is going to have its nabla, and we are going to have this nabla square for each. And plus, each one is going to see a Coulomb potential from the center. Let me write it like in compact form like this. I is equal to 1 to n, some v of Ri, right? I think like even let's simplify. We can write many terms in the Hamiltonian, but let's simplify. Nucleus is fixed. There are a bunch of electrons. Each one has its own coordinates. Like this is R1, this is R2. I don't know. This is Rn, something like that. And the distance to the nucleus. So this is, let's call this electron-proton interaction. But there is also, each electron is going to interact with the other electrons, right? There will be like let me write it like this. There will be now 2 sums, right? For all i's and j's, I'm going to index all electrons, and each electron is going to interact with every other electron. This is the electron interaction, Ri minus Rj. Generally, not to double count, people also put this term. And now you can also have like perturbations, like things like spin orbit coupling. If you have magnetic field, there will be Zeeman term and all these things. But the message is, even in this form, this equation is not controllable, right? Like you can see, even if you have one coordinate, imagine what we had to do. Now we have all of these things. I mean, I cannot even write the Hamiltonian. And for each Hamiltonian written like this, we have to find a wave function, R1, R2, dot, 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 Rn. So this is so-called many-body wave function. And we have to solve H psi is equal to E psi. So that's the job. And there are specialists doing this. There are like also some software specialists developed for other specialists to use. But it is a specialty. So we cannot teach it in this course. Any questions? Should I continue? So the message is we need approximations, and these approximations are going to be very simple. We will not have to go down and solve this equation. At least to understand the periodic table, we'll have just a few simple principles that'll help us a lot, at least to see the periodicity. So basic principles. So first, we are going to minimize energy. So for example, if there is like an empty 1s orbital, we're not going to go and put the electron in the 5s orbital, right? Because you know n is equal to 1 is going to be smaller in energy than n is equal to 5. So it's a reasonable person would choose the first one if it's empty. So that's what it means, the minimize energy. The second one is satisfy Pauli exclusion. So we can only put 2 electrons in a given orbital. For example, 1s can have 1 up and 1 down, but not more. Whereas 2p can have 6 electrons because p can have L is equal to 0, L is equal to plus or minus 1. And the third one is we are going to ignore electron-electron interaction except in screening. So let me explain what this means. I think last time we mentioned this a little bit, but let's repeat that argument, which doesn't hurt. So here's the example for screening. Suppose I take sodium, which is Z is equal to 11, and I have plus 11 charge in the nucleus, right? And now I need to like put 11 electrons in orbitals, and the first orbital is like this is 1s, so this is maybe 2s. How many do I need? 1, 2, 3. Okay, let me make it a little smaller. So this is 1s, this is 2s, this is 3s. So what we need to do, we need to minimize the energy. So what this means is I start from filling the lowest orbital, 1s, up and down, it is filled. 2p, 6 electrons, right? 1, 2, 3, 4, 5, 6, and there's also 2s. In total, 8 electrons. I have 2 plus 8 is 10. Only 1 electron is left, and I'm going to put it in the 3s. But for the 3s electron, this entire system is identical. So this system is identical. If you like erase all the core and all these like complicated configurations and just put inside plus 1 charge and put the electron in the 3s, this is exactly the same thing. So this is what we call the central charge. So charge, nuclear charge is screened, if I can spell, screened for 3s electron. Okay. So if you remember the orbitals with orbital dependence dependence on n. So here is the radial wave functions. Oops. Okay. So you can see 1s is closer. Okay, here is the nucleus. So this is R. So this is the psi n, or let me call it R n L of R, right? So for example, for 1s, n is equal to 1 and L is equal to 0, right? And here is the nucleus. So this is nucleus. And you can see 1s orbital is closest to the nucleus. And then 2s, and then 3s, and then 4s, right? So orbital dependence on n determines electron distance, determine distance to ZE, nuclear charge. And same ends are typically have the same distance. Like we are going to say electrons with same n are in the same shell. Okay. Last time I introduced this one a little bit, but let's repeat, please, to set up the terminology. And because this is the most important thing, we have to give it a name. And this game was given prior to quantum mechanics. So this is n is equal to 1, 2, 3, 4, 5. Then generally we call it K shell, L shell, M shell, N shell, and O shell. Okay. I think we don't use it, but I think some people use it. So maybe spectroscopists, they all use it more often than us. But it's good to know this. So the second thing we need to consider, what is the dependence of energy on L. Right? In the hydrogenic case, there is no dependence, right? In the hydrogen, we have only E of n is equal to minus E1 divided by n squared. But now we are not thinking about hydrogen. Like complicated atoms are going to be complicated things beyond hydrogen. And for that, we need to look at the orbitals. So here is two different, so this is again, this is the distance r from the nucleus, and this is r and L of r. And this is what we plotted with Mathematica last time. I think the code is there. You can go and take it and study if you want. But this is the same n. One is P, the other one is S. And what you can see is that 2s, even though the peak of 2s seems to be a little bit further away from 2p, right? And at first sight, you may think like, oh, 2s is farther away from nucleus. So it's going to have like less interaction energy. But that's not the case, because you can see this little peak inside. And we are going to say that like this 2s leaks inside nucleus more than 2p. And if something leaks inside nucleus more than something else, we say that it has like a stronger binding, right? If you are getting closer, you bind a little bit stronger. And if the binding energy is stronger, ionization energy is going to be larger. Okay? In the d orbitals, let me try to actually even more so than 2p. Right? At first sight, 3s seems to be furthest away, but if you look at the inside, 3s actually has 1 and 2 peaks that leaks inside. That's much stronger than 3d and 3p. Similarly, if you look at 3p, right? 3p, this blue line has a leaking more than 3d line. So what we see is like, as you go to lower and lower L, like smaller L. Of course, we didn't show this, but we are like suggesting based on like reason, right? We are reasoning that that's what it should be because we cannot solve the Schrodinger equation. So the reason is the reasoning suggests smaller L should have stronger binding. Is equal to 4 is also the same. Okay, I think maybe I can put it here. Right, 4s, there are like 1, 2, 3 peaks of 4s. 4p, which is blue, has like 1, 2 peaks that leaks inside, and 4d has like 1, and 4f, which seems to be the closest one, is actually not closest, because it doesn't have as much of a foot inside the nucleus as the other orbitals. Yes, because 4s, the red line, has like a bigger foot inside the nucleus, right? It has more stuff. If you have more stuff inside, you have more at stake, so you are bound stronger. That's what we are saying. So we have to be careful and look at the whole thing, not just the peak. That's generally a common mistake. People just look at the peak and they say, oh, 4f is closest. It's not the case. So by putting, like, what we are saying is like to minimize energy, so to minimize, right, this is the first principle that we outlined, to minimize total E, fill smaller L first. First smaller L and then bigger L. Of course, this is the expectation, and we should always benchmark our suggestions with experiments. Here's the experimental results, right? So this is, if you want, this is the solution of like a many-body problem, right? Nature solves it for us. Even though we can't, what we can do is we can observe the nature and we can learn what the solution can be like. And that's what it is. So this is, what it is saying is like, for example, this is 1s electrons, and I can go and break any electron from any atom, right? This is the state of experiments at the moment. For example, people can go and break 1s electron from hydrogen atom, or they can break 1s electron, so you need to go up like this. So 1s electron from lithium atom, or you can break 1s electron from beryllium atom, right? And what we see is like, here's the 1s as you go from hydrogen to lithium to beryllium to so on, it's getting harder and harder to break that electron because nuclear charge is increasing. But the key observation we did there was like the S electrons should be bound stronger than P electrons, right? And that's exactly what we see. This is the 1s electron orbitals. Whichever atom you look at, 1s electron has require more energy to break than, for example, 2p electrons, right? These are, or like, sorry, 2s electrons require more energy than 2p electrons. So we suggested this based on argument, and it seems like nature is confirming our prediction. Similarly, 3s electrons, right? This line is 3s electron, needs more energy from 3p, whereas 3p electron needs more energy than 3d electron. Basically, smaller angular momentum has like bigger binding, or you can minimize the energy by filling this smaller angular momentum. Also, you can see it goes like almost logarithmically. For example, 1s electron in hydrogen is 1 in Rydberg, which means it's like 13.6 eV, whereas in lithium it is like 3 times more, right? Whereas in, like, for example, beryllium it is 10 times more, and so on. So you can see the most important number is n, and now the second most important, so n was called shell, and the second most important is L. So the same L is called same subshell. So let me write that. Electrons with same L are said to be in the same, here's the keyword, subshell. And electrons in the same subshell have almost the same energy. Of course, there are like higher order terms that we may consider in a little bit, but at the moment they are identical. And based on this suggestion, we can also conclude dependence, energy dependence, E dependence on, for example, ML or MS is tiny. Of course, it is not zero, it is still there, but for most of the periodic table, we don't need to consider that. Good, any questions? So here's the notation that everybody is familiar with. For example, so this is for sodium. Then what we say is like, how do we show which orbitals we are filling, right? We are saying that here is n is equal to 1, here is S, and I put 2 electrons there. Here is n is equal to 2, here is S, I put 2 electrons there. N is equal to 3, S 2, and 3, P6. This is 2, this is 2, P6, and 3, S1. Did I get that right? I think that's right. Okay. Right. So this is, for example, 1s, there's like a single orbital, and I can fill it with up and down electrons. Same for 2s. Whereas 2p, I have like, if you want px, py, pz orbitals, or, right, if you remember the pictures we had of these orbitals, we can consider L is equal to 0, L is equal to 1, or like minus 1. Let me write them in sequence. L is equal to minus 1, 0, and 1. Each one is a level, and I can, what's that? ML. ML? Oh, yes, ML. So this is L is equal to 1, ML is equal to, yes, thank you. So this is up, down, up, down, up, down, and so on.
So we can say first minus 1 ml is filled.
So I'll come to that. Yeah, typically, yeah, you can put them any, like, suppose you had 1 electron, you could put them in any one of them. So based on the arguments we outlined so far, there is like a dependence, but we neglect that. In a little bit, there will be a case where this will be important. Any questions? So then the quantum numbers are going to be important for this. So let me just outline the rules. N can be 0, not 0. N can be 1, 2, 3, dot, dot, dot. L can be 0, plus or minus 1. Okay, not plus, 0, 1, 2, dot, 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 all the way up to n minus 1. ML can be 0, plus or minus 1, all the way up to plus or minus L. And MS can be up or down, or plus a half or a minus a half. So then each MS can have 2, right? And each ML can have 2 times 2L plus 1, right? Because there are 2L plus 1 levels here. And each one I can put 2, so it's 2 times 2L plus 1. And this one we need to sum this, right? This is L is equal to 0 to N minus 1, and 2 times 2L plus 1. I think everybody knows how to sum this series. If not, check it out. It's not hard. And you are going to find 2N squared for each shell. So that's how we fill, and once a shell is filled, so if a shell or a subshell is fully occupied, once you consume a shell or subshell, we say that it is closed. I don't know, I didn't come up with this. Why don't they call it filled? They just call it closed. For example, closed S has 2 electrons. So closed P has 6 electrons, right? 2 times 1 plus 1 is equal to 2, that's why. A closed SPD has 10 electrons. 2 times 2 plus 1 is equal to 10. And a closed F has how many? I think the pattern is kind of emerging. 14 electrons, because it's 2 times 3 plus 1 is equal to 14. And by the way, let's just go back and look at the periodic table. You can see I have 2 columns here, right? This is 2 columns. I have 6 columns here, right? 2 plus 6 is 8. The blue has how many? I have 10 columns, right? D orbitals are going to have 10 columns. And these lanthanides and actinides are going to have, without counting, how many? 14 columns. But you can see the pattern is seems to be matching with the periodic table slowly. So for closed subshell, total angular momentum, and this means L and S, they are total. Maybe I can write it like L plus S. So L plus S is 0. So a closed subshell has 0 total angular momentum. And if the angular momentum is 0, then this means the contribution to total magnetic dipole moment, is also 0, because by gyromagnetic ratio they are related. If the magnetic dipole moment is 0, like then atoms with these closed subshells are not going to see anything else, right? Then atoms with only closed subshells do not interact. So we call them inert, and that's actually what happens here, right? So the inert gases, they have only closed shells and closed subshells, and their total magnetic dipole moment is 0. As a result, they don't have anything to interact with. It's like they just pass through things without any interaction because they are like quite robust. So then, like a little bit difference from alkali metals, like for example, I can, a little bit difference from the inert gases. I can go to, like for example, by adding 1 electron, I can go to alkali metals. Metals. Only a single s electron in the outer shell. And this electron is going to be like, all the other electrons in the lower shells are going to screen the nuclear charge, and this single s electron is going to see a charge approximately +1 from the nucleus, right? So approximately plus E charge in nucleus, but not quite exactly. Maybe I can give an example of this and we can take a break. So here's the example. Again, I think whenever we are unsure, we should go and look at the experiments and then try to see, because like I said, experiments are going to tell you the solution of the Schrödinger equation. Then you can deduce the information you want by looking at the experiment. And in this example, ionization energy of lithium is given from the experiment. Let me write it like energy E lithium is equal to 5.39 eV. What this means is you need to give this much energy to break the electron and make the atom ionized. Then the question is asking what is the effective nuclear charge seen by other electron. So this is what we want to calculate. Of course, we would expect it to be +1 based on the argument I just outlined, but let's just think a little bit more carefully. So in the center, we have +3 charge, and I have to have like 3 electrons to distribute. And the first shell is 1s, and I'm going to have 2s, and I'm not going to need more. And for the 1s, I'm going to have like 2 electrons, and for the 2s, I'm going to have 1 electron. And for hydrogen, I know the energy, ionization energy is what we found from the Schrödinger equation is going to be E1 divided by n squared, and E1 is going to be minus 13.6 eV. For lithium, En is going to be, how do I modify? So Z here is different. So Z is equal to 3 here, right? Whereas Z for hydrogen is 1. How do I, based on what we learned so far, I just copy what I have here and just make a little bit modification to use it for the lithium. What is the difference? Cube?
No, multiply with charge.
Charge? Like Z?
Yes.
Anybody else?
Z squared.
Z squared, right? Why Z squared?
Because in the square root of the E, there is
Yeah.
2 electron times
Yes.
EV.
Yes. So check that. You missed that. So I always miss that too. I always forget to put squared. Thank you. So you just need to put Z squared here. So that's what we expect.
I didn't understand why this.
Because if you look at E squared, what you need to look at E is like you have not E squared inside E, you have E to the 4th, and half of this E squared comes from electron, the other half comes from the proton, and because you increase the proton charge, you are supposed to put Z squared proton. So if you look at the derivation, you are going to see there's like E to the 4th there. And N is equal to 2 for 2s. Let's put that. So this is Z squared E1 divided by 2 squared is given by this E ionization, which is E, let me call it E lithium, and minus is cancelled. Then Z is going to be 2 squared E lithium divided by E1 and square root. Did I get that? Yes. And if you put these numbers, this is 5.39 eV, E1 is 13.6 eV, and this is 2 squared, which is 4. I found 1.26. And this is not exactly, okay, if I can spell, 1, right? Because of this incomplete shielding, or like what we said, some stuff is leaking inside the nucleus that's beyond our simplified description. For that, we account this by looking at the experiment. Okay, then No, this is just a single electron, but electron is like a probability cloud, right? There is like a probability amplitude, and the wave function a little bit is always going to tail inside the nucleus. Whereas in the like this simplified description, we are thinking of it to be outside the electron, right? There's like nuclear charge here inside, and there are 2 electrons with the red, and everything from this third electron is going to be outside of this shell. But that's not the case, right? Because of probability amplitude, there will be some leaking inside. And that leaking is going to see things beyond the screening. That's why screening is going to give a little bit, it's going to be a little bit incomplete.
Shouldn't it be smaller than 1?
No, it is like, if it's smaller, it should be more screening, right? It should like, there is like charge inside, and if you have the screening as we predicted, it should be exactly 1. If it's smaller than 1, there's like less screening. It's not possible to have less screening, right? Right? The charge is always like Z times E, which is, right? But we just decrease it with intervening electrons. Right? So maybe we can give like a 5-10 minute break and we can continue.